Fibonacci search. Fibonacci search is a searching algorithm designed for sorted arrays. And the speciality of this algorithm is that it makes use of Fibonacci numbers. So let us see how Fibonacci numbers are used in order to search an element in an array. There are two things you have to keep in mind while learning Fibonacci search. First thing is, as we already discussed, the importance of Fibonacci numbers, the use of Fibonacci numbers in the search algorithm. And the second thing is that the algorithm that we are going to use is very similar to binary search algorithm. So first let's understand what are Fibonacci numbers and then we'll come back. So what are Fibonacci numbers? Fibonacci numbers, they have a speciality. You can find any particular Fibonacci number by adding the previous two Fibonacci numbers. So how do you form the Fibonacci sequence? The first two numbers in the Fibonacci sequence are predefined. First number is 0 and the second number is 1. How do you find the third Fibonacci number? You add the previous two numbers. So 0 plus 1 will give you 1. So your third Fibonacci number is 1. How do you find the fourth Fibonacci number? You'll add the previous two numbers, that is second and third Fibonacci number. So 1 plus 1 will give you 2. So 2 is your fourth Fibonacci number. How will you find the next Fibonacci number? You'll add 1 plus 2. So that is 3. What is the next one? 2 plus 3, which is 5. How do you find the next? 3 plus 5, which is 8. Next is 13. Next is 21 and so on. So you understood what is Fibonacci sequence. And how can you generalize this logic? You can write like Fn, that is nth Fibonacci number, can be found as Fn minus 1 plus Fn minus 2. What does this mean? You can find the nth Fibonacci number by adding n minus 1th Fibonacci number and the n minus 2th Fibonacci number. So this is the general formula for finding Fibonacci numbers. So the next thing is, in order to use the Fibonacci search, the first thing you want to know is the smallest Fibonacci number which is greater than or equal to n. Well, what is n? N is the size of your array. So let us say you have an array. You want to find the smallest Fibonacci number which is greater than or equal to the size of your array. So let us call it as Fk. Fk is the smallest Fibonacci number which is greater than or equal to the size of your array. After this, where are you going to use this? So we already discussed that the logic we are going to use is very similar to binary search. So if the logic is very similar to binary search, then where are Fibonacci numbers coming in? In binary search, what did you do? You found the middle element. How did you find the middle? You just did low plus high by 2. So that will give you the middle point of the array. Then you checked whether middle element is the one you are searching for. If it is not, then you will eliminate either the left part or the right part, which means at every step you were able to remove half of the search space. That is how you got good time complexity in binary search. So in Fibonacci search, you are going to use the same algorithm with the only difference that instead of finding this exact midpoint, you are going to find some other point which is somewhere over here. And the logic you are going to use for finding that point is mid is equal to, so in case of binary search, it was low plus high by 2. This is what you use for binary search. In case of Fibonacci search, instead of this, you will use low plus, you will start from the low and then you will use f of k minus 2. So what is f of k minus 2? Fk, as we already discussed, is the smallest Fibonacci number which is greater than or equal to the size of your array. That is Fk. And what is Fk minus 1? Which is the Fk minus 1 is Fibonacci number just before Fk. And what is Fk minus 2? Fk minus 2 is the Fibonacci number which is 2 places before Fk. So first thing, you found the Fibonacci number which is the smallest Fibonacci number larger than the size of the array. And then you went 2 steps backwards and you found f of k minus 2. So the significance of f of k minus 2 is it will find a mid. So here I'm using the word mid, but don't be confused. It is not the middle point. I'm just using it because I want you to relate it with binary search. I want you to understand that instead of the middle formula that we use for binary search, we are using a different formula to find the partition point. So here the word mid, don't take it as middle, take it as partition point. Okay. So the partition point is going to be low plus fk minus 2, and this point will come somewhere over here. And the logic is that whenever you have Fibonacci sequence, which says fn is equal to fn minus 1 plus fn minus 2, and if you have anything of the length n, f of n, then fn minus 1, this will be nearly equal to 2 by 3 of fn. So this is how Fibonacci sequence works. And fn minus 2, this will be nearly equal to 1 by 3 of fn. So this is the logic, which means if you take fk minus 2, it will be somewhere at the 1/3 of the array. So the partition point we are going to choose using Fibonacci numbers, which is fk minus 2, is going to be somewhere in the 1/3 of the array, which means on this side there will be 1 by 3 of the total array remaining, and on the right side there will be 2 by 3 of the total array remaining. So I can just show you this with a small example. Actually this works perfect only for larger Fibonacci numbers, but even with smaller Fibonacci numbers we can see the correlation, that is 2, 3, 5, 8, 13, so on. So if you take any Fibonacci number, I'll take 3. If I take 3, previous two Fibonacci numbers are 1 and 2. And what is 1? 1 is 1 by 3 of 3, right? What is 2? 2 is 2 by 3 of 3. So that is how Fibonacci numbers work. So this is not, why did I put nearly equal to? Because it need not always be exactly 2 by 3, but it will be somewhat 2/3 of Fibonacci of n. So you take any number, you will see that relation here. If you take 8, so 8 is near, if you take previous two numbers, then for example 5 is nearly 2/3 of 8. So it is not exact, but somewhat 2/3 of 8. Similarly, if you go 2 digit backward from 8, 2 numbers backward from 8, you get 3. 3 is nearly 1/3 of 8. Okay. So this is the logic we are using. So you can somewhat see it like you are choosing a partition point which is at 1/3 of the total size of the array. Let us understand what is the logic we are going to apply it now. So the logic is something like this. You have the middle point which is chosen by this formula. Once you have the middle point, you will first check whether the AR of array of mid. So it is not mid, it is the partition point. If that is same as target, same as the logic of binary search. If it is same as target, you will say search successful. You found the value at the index mid. If it is not, if AR of mid, if this is less than target, that means the target value is on the right side, right? Because this is the middle element and your target is larger than this. And we already said this works only for sorted arrays. So given that the target is larger, you know it is on the right side of the array. So what are the changes that you'll have to make to your Fibonacci numbers now? Because next time when you calculate mid, you have to make changes so that Fk will remain as a Fibonacci number which is almost the size of this new partition. So previously your Fk was of the size of n, right? You found Fk as the smallest Fibonacci number larger than or equal to n, which means you were somewhat approximating that Fk would be n, almost n. And then you were finding 1/3 the point of Fk and dividing it. So this time you understood you have to go to the right side of Fk, and which means the left part is eliminated and the only remaining search space is on the right side. So you have to get a new Fk which is of the size of this right side. So how do you find this? In order to find this, you just have to decrement Fk by one Fibonacci number. Why is it? Because you know Fn is equal to Fn minus 1 plus Fn minus 2. And if this total distance is Fn, then what is 2/3 distance? It is fn minus 1, the just previous Fibonacci number. So what updation you have to do now? Whatever was previously your fk Fibonacci number, that has to be substituted with whatever previously was fk minus 1. So whatever was your Fibonacci number, you go one digit downward. So if previously your sizes were 0, 1, 1, 2, 3, 5, 8, 13, and let us say previously your Fibonacci number was 13. This time, instead of 13, you will choose 8 as your Fibonacci number. So fk minus 1 will be 5, fk minus 2 will be 3 in the new case. Okay. And one more thing you have to do is you have to reset the low value, or you can call the offset value, whatever. The low value you have to reset as the new mid, as a mid element that you got, because this part you are going to eliminate from the array. So this is what you have to do in case AR of mid is less than target. So what are the two things? One is low value has to be updated. How do you update the low value? The low value has to be updated as your mid. Okay, whatever was your previous mid, that will be your low. And what will be your Fibonacci numbers? How will you update? You will update Fibonacci number, whatever I'll call f as fk. So fk equal to fk minus 1. Then what you have to do? Fk minus 1. This is equal to fk minus 2. That is, you are going one step backward. And how will you find fk minus 2 this time? In order to find fk minus 2, you use the same logic, because you updated fk and fk minus 1, and now you know this fk is supposed to be fk minus 1 plus fk minus 2, which means fk minus 2 will be fk minus fk minus 1. So this is the logic you have to use. So you understood this step, right? Because you updated fk and fk minus 1, and you know from here that fk is equal to fk minus 1 plus fk minus 2, which means fk minus 2 is equal to fk minus fk minus 1. So that is the logic you are using here. So this is what you will do in case target is larger than AR of mid. If AR of mid is larger than target, in this case, your target is on the left side of the mid. Whatever is your mid, on the left side you have the target. And this means you can eliminate 2/3 of the array. Only 1/3 is remaining, which means you can't even choose the Fibonacci number which is just before, because that will still be having 2/3 the size of array. But now you need only 1/3 the size of whatever array you were having, which means you have to down Fibonacci numbers by 2. That is, if fk, whatever was your previous fk, should now be substituted by fk minus 2. Okay, you understood this, right? You have to substitute by fk minus 2 in this case where target is lesser. So how will you substitute with fk minus 2? Then your fk, that will become fk minus 2. This is straightforward. But how will you find fk minus 1? Because fk minus 3 is required for this. For this, you will use the logic that we used previously, that is fk minus 1 can be updated as whatever is your fk minus 1 minus fk minus 2. Okay, because here you are using the fk minus 1 value from the previous step. That minus fk minus 2 should give you whatever was fk minus 3. So in place of fk minus 1, you actually want fk minus 3 value, which you got by using this formula. So now your fk and fk minus 1 are already updated. If that is updated, then fk minus 2 can be found by the same way we did in the previous step. That is, you can do fk minus fk minus 1. So this is the logic we are going to use in Fibonacci search. So let us write the pseudo code and understand this. And one more thing I have to clarify here, that is, you can have this doubt of why should you use these Fibonacci numbers? What is the logic here? Why can't you simply choose 1/3 of the array as a midpoint? Like, if anyway you are going to choose a point which is at 1/3 the part of the array, why do you choose the Fibonacci numbers? Why do you cause all these problems? You simply take 1/3 and choose that as the midpoint. That's easier. So why are we not doing that? The reason is this, that if you simply want to choose 1/3, 1/4 or whatever, you could have simply gone with binary search itself, which is choosing one by 2 of the array. So there is no point in simply choosing some random numbers like 1 by 3, 1 by 4 and calling it by different names. It's all the same search algorithm, right? So you could have used binary search itself. So here the significance is not of 1 by 3. The significance is of Fibonacci numbers because there is something called as golden ratio. You denote it as phi. The speciality of this golden ratio is that it is proven that golden ratio, it is a unique number which simplifies your mathematical solutions. So the logic is like this. The golden ratio, if you draw a line and you divide it into two parts such that your, let's say, first part is called A and second part is B. So this length is B and the first length is A. Then the total length divided by the larger part and larger part divided by smaller part will be the same. So this is the logic behind golden ratio. So okay, I'll show it here. In golden ratio, if you have total length, that is A plus B divided by larger part is B here. If this is equal to larger part divided by smaller part, so B divided by A. Both these will be equal. If both these are equal, then this ratio will be phi, which is the golden number. So golden ratio. And the value of golden ratio, it is an irrational number. So it goes something like 1.618 and so on. So it is an irrational number. You can't simply write it down. Another way of understanding it is that it is the equation solution for the equation phi square equal to phi plus 1. So that's also another definition for golden ratio. So the significance of golden ratio is that even though the time complexity would remain as order of log n, which is same as binary search, but golden ratio is supposed to be more mathematically refined and it is supposed to give a better performance while dividing it by golden ratio than dividing it in the middle. So that is why dividing it by 1 by 3 doesn't make sense, because you could have simply divided by 1 by 2 only. But dividing it by golden ratio makes sense because golden ratio is proven to have mathematical significance, that it will improve the performance of these sort of mathematical algorithms. So exactly dividing it by golden ratio makes sense. The next question is, how is Fibonacci number in this scenario? How is Fibonacci number related to this golden ratio? So the reason Fibonacci number comes in is, Fibonacci numbers have a speciality. That is, if you do limit n tends to infinity, that is if you consider very large numbers, if you do fn plus 1 divided by fn, that is Fibonacci number n plus 1 divided by fn. If you do that, you will get golden ratio. This is the speciality of Fibonacci numbers, which means what were you doing in the array? In the array, you were finding a point such that this part is your fn minus 2 and this part is your fn minus 1. So here you are dividing this array by golden ratio only by using the logic of Fibonacci search. So using Fibonacci numbers, you are able to implement division by golden ratio. So the reason we are using Fibonacci numbers is that you want to divide it by golden ratio, and in order to do it by golden ratio, you need Fibonacci numbers because they have this property that limit n tends to infinity, Fibonacci n plus 1 by Fibonacci of n is the golden ratio. So when you divide it into two parts such that one part is of the length fn minus 1, other part is of the length fn minus 2, then you are dividing it by golden ratio, right? So this is why Fibonacci search is more efficient. It is supposed to be providing a better output, better time complexity, not time complexity. Complexity would remain as order of log n, but it is supposed to give better performance. It is supposed to complete in lesser time than binary search because of this golden ratio division. Okay. So now let us go to pseudocode. I wanted you to understand why we are using Fibonacci search, because otherwise if you simply understand that it is 1/3 of the array it doesn't make sense to use all these Fibonacci numbers. You could have simply divided by 1 by 3, right? So that is why I explained it. So let us go to the pseudocode and understand Fibonacci search algorithm. So we'll write the pseudocode for this. Fibonacci search. I'll write as FS for Fibonacci search of array and target. So in this array, you want to find this target value. So what are the variables that you will need? First thing is you want the length of array. So I'll point it as n is equal to length of array. This is the first thing that you have. Second thing, we know we need 3 Fibonacci numbers. The Fibonacci number, which is smallest Fibonacci number, which is larger than n. Then the Fibonacci number just before that and the one just before that. So we'll find out all those Fibonacci numbers. So what we'll do now, we'll have initial Fibonacci numbers defined. So you will have f. So I'll call them as f, f1 and f2 in order to denote fn minus 1 and fn minus 2. Okay. So f is the Fibonacci number, main Fibonacci number, which is the smallest Fibonacci number larger than the size of n. F1 is fn minus 1 and f2 is fn minus 2. Okay. So your f2 is the smallest among all these. So we'll start f2 with 0. And what will be f1? F1 will be 1 because your Fibonacci sequence is 0, 1, 1, 2 and so on. Okay. And what is your f2? Okay. What is your f? F will be f1 plus f2. Okay. And what more do you need? What other variable do you need? You will need the low value. Okay. Low value of the array. That is the lower index. Okay. So this much are the variables that we'll need. So first thing, we have to find the Fibonacci number, which is smallest but larger than the size of array. How do you find it? You do a while loop. Okay. You do while f is greater than 1. F is greater than less than n. So you want to find f such that f will be greater than or equal to n. So till that point you have to keep looping. What will you do in each iteration? You will find the next Fibonacci digit. So how will you find the next Fibonacci digit? You have to update f2 as whatever was previously f1. So you went one step up. What will be your f1? F1 will be whatever was previously your f0. And what is the third thing? How will you update f? F will be f1 plus f2 because that's how Fibonacci sequence is formed, f1 plus f2. So when you do this, you will get the next Fibonacci number. Then when this loop is run again, you will get next Fibonacci number and so on till you find a Fibonacci number which is greater than or equal to n. Whenever that happens, you will come out of this loop. So at this point, you reached fk, that is whatever is the Fibonacci number you need, which is larger than or equal to n. Which means you can now start the Fibonacci search algorithm. That is whatever is similar to binary search because you now know how to find middle point. So how will you write that while loop? In that while loop, you will have while your f Fibonacci number is greater than 1. So you'll understand why this is f greater than 1 because you will keep dividing the array into partitions and you'll eliminate one among these two parts. And you have to continue this till the point you have a part which has only one element. Okay, so that is what you're denoting as f greater than 1. That is, if your Fibonacci number is greater than 1, that would mean your partitions will be fk minus 1 and fk minus 2. So if f is greater than 1 and you are coming out of loop when this is not right, that is, you'll come out of loop whenever f is equal to 1, which means f1 should also be 1 and f2 is equal to 0 because first three Fibonacci digits are 0, 1, 1, which means there will be only one element in the array. So that is what you are going to check here. So whenever f is greater than, till the point f is greater than 1, what do you have to do? You have to find the midpoint. So your midpoint, what is the formula for midpoint? You have to find minimum of low plus f2. This is one thing, or n minus 1. Why am I having this minimum? Because it may so happen this value low is the lower offset, lower index of the array plus f2. This may go beyond n, but you only have the largest index in the array as n minus 1. So that is why I am doing minimum of low plus f2 and n minus 1. That is your midpoint. So that is just to catch the worst case. Okay. So at this point you got the middle point, that is 1/3 point of the array. That is what you found here. What are you going to do now? You are going to check whether the target value is found. So if AR of mid is equal to target. If it is equal to target, what would you do? Same thing that you did in binary search. You will return mid by saying I found the value, target value, and it is present in the index mid. What is the other condition? Else if AR of mid, if AR of mid is less than target. In this case, what does it mean? If AR of mid is less than target, that means target is larger than the partition element, which means target is on the right side of partition element. So when it is right side, you know there are 2/3 size, that is of 2/3 size. So you have to down the Fibonacci number by 1. So you have to go 1 Fibonacci number down. So what is the logic that we already learned? In order to go 1 Fibonacci number down, you will make whatever is your main Fibonacci number, that is the previous one, f1. And what will be your f1? F1 will be f2. And what will you do to f2? F2 is equal to f minus f1. So how did you do this f minus f1? Because you already know f is equal to f1 plus f2. This is the Fibonacci sequence. So if you don't know f2, you will do f minus f1. So that's how you found Fibonacci. So this can be done only after updating values of f and f1. Okay. And what else is to be updated? You also have to update your low value. Your low value will be updated to mid. Why is this done? Because you found that the target value is larger than this, which means low value is no more the starting point of array. It is new mid will be a low value, so that your search space is decreased. So this much is to be done when AR of mid is less than target. Else, I'll still write else if, so that you clearly understand what is the condition here. AR of mid is greater than target. If AR of mid is greater than target, which means target is less than AR of mid, target is on the left side, which is having only 1/3 elements, which means you have to go 2 Fibonacci numbers down. So how do you go 2 Fibonacci numbers down? Your f will be f2 instead of f1. And what will you do with f1? Your f1 will be f1 minus f2. Why is it f1 minus f2? This is the logic. You initially had f1, f2, 3 Fibonacci numbers. What did you do now? You updated this f value to f2. So this value is now f2. What was previously f2? That is your new f. But your f1 has to be updated with whatever would be f3. Whatever was previously f3. But you don't know what is f3. So how do you still find out f1? You will do f1 minus f2, because your f1, new f1 plus whatever be your f2, that should be that should be your old f1, because your old f1 is 2 digits from here. So if you add this and f3, you should get old f1. So the new f1 will be old f1 minus f2, because that will be f3, right? So that is your new f1. So your new f1 will be old f1 minus f2, which is your old f3. Okay, that is the value. And what is the next thing? Next thing is you have to update f2. And f2, how do you find it? Again, same thing. Previously you found it f minus f1. The same thing you will do, f2 equal to f minus f1. Okay. So why f minus f1? Because by Fibonacci formula, f is equal to f1 plus f2. So you already finalized f and f1. So using that you will find f2. So these are the 3 conditions that you have to handle. And after this, if it is coming out of the loop, that means f is equal to 1, or maybe f is less than 1. Both cases are possible. So considering f is equal to 1, you in ideal case, it should be f1 also equal to 1 and f2 equal to 0. In this case, you will still have one element left in the array. That is, one element will still be left to be scanned. So it is possible that that element may be the target element. So in order to catch that, you want to do an if case. If, what are the conditions? One is f1 should be equal to 1, f1 equal to 1, and what is the other condition? Whatever is the value in that one element in the array, that should be target. If then you should return. Okay, so AR of whatever is your low plus 1, this should be equal to target. If this is equal to target, then what will you do? You will return the value of low plus 1. So return low plus 1, whatever is the index. Okay, so this is the actual condition, AR of low plus 1 equal to target. In order to make sure that this AR of low plus 1 exists, for that you have to make sure that there is at least one element left in that array, in the search space. That is why you are having this condition of f1 equal to 1. And if none of these catches, if it comes out of while loop and even this condition also fails, that means the searched element is not in the array. So in that case, you will return -1. So you should do return -1 if none of these catches, all these fails. So this is the Fibonacci search algorithm. So what is the time complexity and space complexity here? Time complexity is order of log n, because it's the same reason why binary search is log n. That is, instead of 1 by 2, you are doing almost 1 by 3. It is supposed to be mathematically more efficient, but time complexity will remain order of log n. And what about the space complexity? In this complete algorithm, we didn't use any extra space. That these variables are all constant spaces. There is no extra space used. So your space complexity is order of 1. That is constant extra space. That is, it is not varying with the size of array. So this is it about Fibonacci search. Time complexity is order of log n and space complexity is order of 1.